Hello and Assalamualaikum. We are from Group 8. We are going to present about differential scanning calorimetry DSC and differential thermal analysis DTA. So the group members of us is first Chiu Yukian Janice, second Muhammad Adi bin Ayub, me, and third is Putra Fayat Khalaf bin Muhammad Arifin. Hello. So first we are going for the introduction to DTA and DSC. What is differential thermal analysis DTA? The differential thermal analysis DTA is commonly used to determine the thermal stability of polymer. For the definition, DTA is a technique in which the difference in temperature between the sample and a reference material is monitored against time or temperature, while the temperature of the sample in a specific atmosphere is programmed. To make it short, for DTA, both sample and reference are heated by the same heat source, and the difference in temperature delta T between the two is recorded. When a transition occurs in a sample, a temperature lag will show as an endothermic or exothermic depends on the transition. DTA data only report the softening, which is phase transition temperature of polymer. So in this diagram, this is diagram of DTA. We can see there is sample and another one is reference. So when sample and reference are heated by the same heat source, the difference in temperature delta T between the two is recorded. So we are going for the more detail about DTA in the next slide. So how about DSC? What is differential scanning calorimetry, DSC? DSC is the generic term for the following two measurement methods. First is heat flux DSC, a technique in which the temperature of the sample unit formed by a sample and reference material is varied in a specific program, and the temperature difference between the sample and the reference material is measured as a function of temperature. The second is power compensation DSC, a technique in which difference of thermal energy that is supplied to the sample and the reference material per unit of time is measured as a function of the temperature to equalize their temperature, while temperature of the sample unit formed by the sample and reference material is varied in a specific program. In this diagram, we can see the DSC diagram. So we are going for DSC in the next slide. To make it short, for DSC, sample and reference are provided with individual heaters, and energy is supplied to keep the sample and reference temperature constant. The electrical power difference between sample and reference is recorded as d delta Q over delta T. DSC report the softening phase transition temperature of polymer and also provide the amount of heat involved in the softening process. The DSC is more preferred in the polymer characterization because the precise control and measurement of heat varied in the heating process. DSC enables the measurements of the transitions such as the glass transition, melting, and crystallization. Furthermore, the chemical reactions such as thermal curing, heat history, specific heat capacity, and purity analysis are also measurable. Recently, with the development of the highly functional polymetric material, these thermal properties analysis needs are increasing dramatically. DTA and DSC detect the temperature difference between the sample and the reference. However, DSC can perform the quantitative measurement of the amount of tip of heat on top.
Zhou Xian Janice. I will talk about the instruments of DTA and DSC and how do DTA and DSC work. In DTA, it contains sample and reference holder, furnace to heat the sample, furnace temperature controller to increase the furnace temperature steadily, furnace atmospheric control system to maintain a suitable atmosphere in the furnace and sample holder, and then the recorder. How does DTA work? At first, the sample and the reference are placed symmetrically in the furnace. Both sample and reference are heated by the same heat source. The furnace is controlled under a temperature program, and the temperature of the sample and the reference are changed. During this process, a differential thermocouple is set up to detect the temperature difference between the sample and the reference. In DTA, there are two thermocouples are needed because one of the thermocouple measures the temperature of the sample and the another one measures the temperature of the reference. So when a transition occurs in a sample, a temperature lag will show as endothermic or exothermic depends on the transition. The temperature difference between the sample and the reference is recorded as d delta T over dt. In DTA, a graph of the temperature difference against temperature is plotted. As you can see in the graph, the temperature difference due to the endothermic reaction is shown as a negative direction. This is because heat is absorbed and the temperature decreases. So for the exothermic reaction is shown as a positive direction. It means that heat is released and the temperature increases. Now is the turn of DSC. The DSC instrument is similar with the DTA. It also contains sample and reference holder, furnace, sensors, temperature controller. The temperature controller in DSC is to maintain the temperature of the sample and reference at the program value. How does DSC work? In DSC, sample and reference are provided with individual heaters and energy is supplied to them. The sample and reference are kept at the same temperature as it changes across the gradient. As the sample undergoes phase transition, more or less heat is needed, which allows for phase diagram to be created from the data. DSC measures the amount of heat that is needed to increase the temperature of the sample and the reference across a temperature gradient. The basic principle of DSC is when the sample undergoes a physical transformation such as phase transition, more or less heat will need to flow to the sample than the reference to maintain both at the same temperature. By observing the difference in heat flow between the sample and the reference, DSC are able to measure the amount of heat absorbed or released during the transition. The electrical power difference between the sample and the reference is recorded as d delta Q over dt. In DSC, a graph of heat flow against temperature is plotted. In the graph, the curve can be used to calculate the enthalpies of the transition. This is done by integrating the peak corresponding to a given transition. As you can see in the graph, there are three transitions, which is glass transition, crystallization, and melting. Just now, I did mention there are three transitions observed in the DSC graph. The first one is glass transition. Glass transition may occur as the temperature of an amorphous solid is increased. This transition appears as a step in the baseline of the recorded DSC signal. This is due to a sample undergoing a change in heat capacity. As the temperature increases, an amorphous solid will become less viscous. The second is crystallization. At some point, the molecule may obtain enough freedom of motion to spontaneously arrange themselves into a crystalline form. This is known as the crystallization temperature. This transition from amorphous solid to crystallized solid is an exothermic process and results in a peak in the DSC signal, in which the peak is in positive direction as the heat is released and the temperature increases. The last transition is melting. As the temperature increases, the sample eventually reaches its melting temperature. The melting process results in an endothermic peak in the DSC curve, in which the peak is in negative direction as the temperature decreases.
Hey guys, so let's go to the example of differential scanning calorimetry. The first one, heat flux DSC. Heat flux DSC contains of two types. The first one is this type measuring system with solid sample support, and the second one is cylindrical type measuring system with integrated sample cavities. If you are looking at the picture, the left one is this type of measuring system and the right one is the cylindrical type of measuring system. Interesting, right? So the next example of differential scanning calorimetry is the power consumption of DSC. The power consumption of DSC is using heat compensating calorimeters. The picture below shows the power consumption diagram. Interesting, right? So for the example of application of differential scanning calorimetry, is one of them is identification of substances, the phases behavior, and the second one is determination of the degree of crystallinity. So the two picture or diagram shows the DSC curve for the application. The right one is for determination of degree of crystallinity and the left one is for the identification of substances, the phases behavior. For differential thermal analysis, there are a lot of applications. One of the application is determination of high-low inversion behavior of microcrystalline quartz crystal, and the second one is determination substitution of calcium ions by barium ions and lead ions in argonites. So guys, you can see the example of the curve graph over there. The left one is for the first high-low inversion and the second one is for the substitution of calcium ion and etc. Thank you very much.